in the first part, we saw that the study of the closure of the entropy region is basically the same like the study of subgroups of a symmetric group. Symmetric group, of course, contains all kinds of subgroups, and it's been long. It's been more than 100 years since people study symmetric group, and up to now the field is active, and representations and asymptotics of representations is of big interest. And in the second part, I'd like to expose another approach to characterize the closure of the entropy region, and it's through matroids. So I will repeat the definition of polymatroid and matroid, and then I will try to say something about matroid and prove one theorem I did earlier, and in the last part I will do more about the convolution. So polymatroid, I have finite set usually of n elements and a function on subsets. I probably needn't repeat the whole definition, just to say that it's a function I to hi empty set is always 0, is non-decreasing. And I will write the submodularity because I'm going to use it. And it's submodular. This implies that it's non-negative. And the most interesting functions are integer valued. So if h is, this is polymatroid. And if h is integer valued, and bounded by cardinality, then it's matroid. So and as we all know, almost entropic, if G is almost entropic, then G is a polymatroid. And the class of polymatroids I denote simply by H. So everything starts for polymatroids, and those indices specify subsets. It's not well written. So this non-decreasing is for me like first derivative positive, yes, and this is like convexity. And there are analogs between the continuous, between the convex analysis and this kind of discrete analysis. Okay, there are only finitely many matroids for given n, yes, because the constraint makes them. And this is a structure that has been studied since '36. And my favorite reference is the book by James Oxley that came in second edition a few years ago, and it's a big book and it's comprehensive and it's nice. But there is nothing about entropy in the book. Okay, so what are the matroids good for? Certainly we know this almost entropic region is convex, so the question is what are the extreme points? Or because if we have extreme points in a convex set, then we can combine everything inside. And less simple question seems to be what are the extreme polymatroids? But even that question is somehow hopeless. in general, I have no good idea. But anyhow, maybe we can recognize on some extreme points that are of some use, and matroids turn out to be good candidates for such extreme points. Yes. So that's what I want to expose now. So I have to introduce the connectivity. So H is connected. Polymatroid is connected if it cannot be split into two independent parts. That means whenever hi plus h n minus I is equal to hn, then I is empty or n. Yes. This is actually equality here, because intersection is empty. Yes? And if this happens for a non-trivial partition into two blocks, then it's by some modularity directly that every set splits into two parts in this way. So then I could define maybe H1 if no I is proper. Let's say not empty and not n in this. Then I can define H1 like maybe in J, Hi intersection J, and H2 on the second part of I. This is on I, and on the second part and then H is equal H1 plus H2. And they are genuinely different, because this is 0 outside of I, and this is 0 in I. So they are certainly H1 is different from H2. And I combined H, so H is not extreme in H. In such a situation, H is not extreme. So we have to avoid non-connected things. So now assume a connected matroid. For matroid, I use instead of HR, because this function is called the rank function. So if NR, well, maybe NR is a connected matroid, then R is extreme in the cone of polymatroids. I don't know whom should I attribute the result, because that is probably a piece of folklore. But I referred to some paper by Nguyen, 78. And he has a necessary and sufficient condition for integer-valued polymatroid to be extreme. Okay, but the condition is quite complicated. It applies. Well, I mean, it's necessary to do expansions and multiples. I will not go into that result because I want to prove this, and this has a simple proof, and that should be a part of Oxley book, I would say. It's nothing with entropy, and. I cannot use that result effectively by Nguyen. But this is nice observation to remember, and it has a reasonably simple proof. So proof. What to do? There are two observations, yes. First observation is that yes, I have to tell a bit more. Who is not familiar with matroids? Everybody is familiar, yes? Then it's okay. Then I have I take independent set, yes? Independent set means it has the rank equal to cardinality. And I am assuming that, yes, I am assuming that R from the very beginning is a combination of two polymatroids. And I want to prove that this is a multiple of R. Yes? So these are polymatroids. Matroids. I take I independent. This is sum of Ri. Yes. This is a sum of Fi plus Gi, because it's combination. And this is greater or equal than Fi plus Gi. And this is Ri, which is again cardinality. So I must have equality here for all I. And what can I conclude? If I have equality here, then I conclude that Fi is the sum of Fi. Yes, I should have told that if this happens for n, then F is called modular, yes. That should be part of the definition. No place for that. Polymatroid is modular, yes, that was connected, and H is modular if Hn is sum of Hi. Hn. I write, well, sometimes I write n, yes, because I'm accustomed to capital N. So if I is independent, then the component f must behave like a modular function on I. So it's first observation, and second observation is if I is a subset of J, and the rank doesn't increase. So this is Rj. Then what can I conclude? I will again write it through, and this is F I plus Fj plus the Gi. Now this is equal to that, and this is less or equal than Fi plus G, Fj plus Gj. Oh, F should be there, yes. Oh, sorry, Fg. But yes, this got changed, and this is okay now, yes. It's the usual thing that people think one symbol, write second, and it should be third. So this is Rj. And then I have to have equality here again. So I conclude that Fi is equal to Fj. So two observations. If I is independent, then F behaves modularly on the independent set. And if rank doesn't increase, then the same with F, with each component. Yes. And what can we conclude now? Yes, now we have to look at the circuit. Circuit is a special set. It's not independent, but every proper subset is independent by definition. So that means R C is R C minus I, and this is cardinality of C minus 1, yes, for every element of circuit. So each proper subset is independent. So I now, the component must behave modularly. Then I know that the sum of Fj over J, or Fk, let me write, over K in C minus I is F C minus I. And this is from by observation 1 from this equality. And by observation 2 from this equality, I get that this is Fc. Because rank doesn't increase, so the same with F. And then this is for every I in C. So if I look at such sums, I conclude that Fi is equal to Fj for every I j in the circuit. Yes? And this is nice because this shows that this F should be maybe T. This F behaves exactly the same way like R on the circuit, up to some multiple, yes? So I conclude from that and modularity that F maybe K is the same like rank for K in a circuit. Not R, I have to write here T, some T. And this T depends, of course, on the circuit. For given circuit, maybe I write TC here. So this is what we want. We want to conclude that the component is a multiple of R. And we are now able to do it on a circuit. And now that now the assumption comes, the matroid is connected. So there is a lemma saying that matroid is connected if and only if every two elements are contained in the circuit. But this means that all that TCs are the same. So TC doesn't depend, not depending on. So at this moment we know that F is equal to T times R on sets that are, well, either independent, because the things sum modularly on sets that are independent means equality here, yes, or on circuits. Connected, and that's quite enough, because if we take any set, any subset, maybe J, then I can find I independent subset, and the rank is the same. So rank J is the same like the rank of I. And if they coincide on I, and the rank doesn't increase, that's this case. So they must coincide also on a bigger set. So then I can conclude that F is equal to TR. And that's what I want, yes. So it's only a combination of submodularity, non-decreasingness, with independent sets and circuits. It's not a difficult proof. That's why I think the people must have done it independently many times. Okay, then next theorem I want to expose is by me, and the natural question is: this is extreme in H. So what about an entropic point on that? So I have NR connected. And now I am asking, does there exist positive T such that T times R is entropic? So theorem says theorem describes what's going on in such a situation. Yes, must be intuitively it's extreme situation. The distribution or the partitions must be very special. Yes, the distribution is not so special because well, it is special, but it's something like uniform. So this is theorem I did long time ago. And it's not a difficult theorem. I mean, it's something like that. I did it probably in some local proceedings, 92. And theorem says if this is connected and this happens, entropic from variables psi I sitting on omega p, omega finite and p positive, yes, p adjusted. Then so if we have indeed an entropic point on such a special extreme ray of the cone of polymatroids, then the variables must be very special. And this T must be very special. So T, there exists T positive. There exists D integer such that T is log D. And omega has D2 Rn elements P is uniform and if I create the partition from the corresponding subset of partitions, then the partition is very special. So this has D2 Ri blocks of the same size. That's it, yes. So example. I take omega with 4 elements, omega, and 3 partitions, 1, 2, and 3. These are 3 partitions, yes. So D is 2, and matroid is uniform on 3-element set of rank 2. So these are, this is not a good example because it's linear. These are 3 bits that sum to 1, to 0, yes. And they sit on a space of 4 elements. This is first bit, second, and third one. But it illustrates what's going on in general. And this is combinatorial, kind of combinatorial reduction. So I'd like to prove this because it's also a short proof. The trick is, again, to take a circuit. C is a circuit. Yes, one more assumption is missing. The rank must be at least 2. Because if the rank is 1, then I would have included that case with R1n, which contains identical variables with any distribution. It's nothing about uniformity. So this will also, okay, the circuit must have, well, there is a bit subtlety because some elements may be in parallel. So, okay, then circuit, there are 2 possibilities. Either circuit has 2 elements or more elements. In that case, we know that the entropy of psi I is entropy of psi j and is entropy of both. So each is a function of the remaining because this is P times rank I union j. Yes, and rank and this is T times Rj. So I'm doing now the first case. So both variables are the same, and if I can conclude something about one of the, if one is uniform, then the second is uniform. So don't study this much because this is like repetition of variable in the whole thing. So I can assume that such thing doesn't occur, and then the matroid is called simple. It's like not having parallel edges in a graph. It's the same situation. And for the second case, maybe the circuit is very simple, from 1 till m. M is at least 3. So I can pick up, and now I know that the rank of 1m is 2. Which means the first 2 variables are independent. So I can take x1, value of first variable, and xm, value of the last variable, and they may take arbitrary values. I mean, so probability of x1, xm is positive for every such thing. I should have written it here. This probability is positive, then I can plug in some other values in between. And have the probability positive. That means they exist x2, etc. And what's going on now? Now we know that this is a circuit, so entropy of C is the same like entropy of C minus 1. Yes, because rank doesn't, entropy is TR. Yes, entropy is T times RC. This is the entropy. that means each variable is a function of the remaining variables, and therefore this probability is equal to p x1 till x minus 1, and it's the same like x2 till xm. And one more, we know that this is a proper subset of C, so variables must be independent. So this is product. So this is p x1 times p xm minus 1. This p x2 times p xm. And now I cancel everything, and I get p x1 equal to p xm, which says, and that was for every state of first variable and nth variable. And this is quite a strong statement. I can conclude that the state spaces are of the same size, and the probability must be uniform. So if the and this must be 1 over the well, the notation is not quite okay because I should write here something like marginals, but you understand, yes. So I now can conclude that psi1 psi m is uniform as a vector. And this was for first and last variable, and the circuit is completely symmetric, so this is for all variables. So then I can conclude that all xi are this cardinality, these cardinalities in a circuit are the same. And then I use the same lemma like here. Every 2 points are in a circuit, and then all cardinalities are same. So then all cardinalities are the same, and I denote the common cardinality by D. This is the D here. Yes, variables are non-constant, so that's why D is at least 2. And then I can conclude T is equal to log D because this is entropy of each individual variable. And then what do I next? Well, the same kind of trick like here. For independent sets, things are independent. So if each variable was uniform and they had the same number of values, and then for I independent, psi I has D2 cardinality of I values and is uniform on that values. And the same argument with if the rank doesn't increase, then the remaining are functions. And well, so I will not repeat the same story, but this is the last statement of the theorem. That vector has so many blocks of the same size. Yes, which means the variable takes so many values with the same probability. Yes?
Do you understand correctly that from this argument we get that the extreme array for 3 variables corresponding to these entropies there are isolated points corresponding to uniform distributions, but not the entire
Yes, in the entropic region, it means, what does it mean, yes, in the entropic region? If I look at this R, this ray generated by R, then I can get here only log D. This might be entropic point for some D integer. So log 2 or log 3 or maybe only some of them, yes. It doesn't say that each D is good, yes. The theorem says only if this happens, then it's somewhere for some D, well, the partitions work, yes. And then of course, if this matroid is Vamos, then there is no D, yes. Or if this, I proved in the paper 98 that if the matroid is Fano-matroid, which is this one, then D must be power of 2. And this is not a linear result, it's a result on combinatorics. And if it's not non-Fano, then the D must be odd. So such things can be done. And it becomes, for each single matroid or small matroid, one would like to know what are the possible Ds, and this is a terrible problem. Maybe I should write a problem. Given a matroid, find all D such that log D times R is entropic for a matroid NR. What is my time? Till the end? 10 minutes, yes. Yes, okay, then I will start with what can I say? I call matroids of this form partition representable because it's about partitions. I mean, the probability disappeared. It's everything about the combinatorics. So such a matroid is partition representable or simply P representable. But other people may like a different terminology, like secret sharing matroid is the same, or almost there are almost defined codes and that correspond to this setting. And okay, things are renamed several times.
Are you saying that all almost defined codes are partition representable matroids?
Almost defined codes. If you take almost defined code, yes, it's a row. It's a matrix with rows, yes, and you put the uniform distribution. For each set of columns, you compute entropy, and that is the same situation. Basically, the same situation, almost defined. This is notion by Simonis and Ashikmin, from that paper. That is not linear, yes, or multilinear. That's the open problem, yes. Problem 5. I have it on my slides, yes. Find matroid that is P representable and not multilinear. Multilinear means that well, that these partitions are not in that this is not a linear space, and these are not partitions into into cosets of subspace.
I think in network coding it's called vector.
Or vector, yes, or vectorial, or okay. This is a problem since Simon is Ashikmin, yes, because they found non-Pappus matroid is not linear, but it's multilinear.
Do you know how they found it?
By computer, I guess. They provide metrics. And for each variable, you have two columns. So it's like 18 columns grouped in couples. So even for very simple matroids like this one, I have no idea what is the complete classification of such structures. Okay, then I will, in the remaining part, define the convolution. Well, and if you encounter a problem like this, which is hopeless, and then the natural shift is to do the things approximately, like with the closure of entropy region. So maybe we don't want to have it exactly multiple of a rank, but maybe approximately. So the question is, then the next natural question is, what is whether given a matroid, there exists T positive such that T times R is almost entropic. So it's well approximable. But we had this lemma 1, so the T doesn't matter, because if it's approximated, so I can say immediately T, R. Yes, it's the same question. And this will be the topic for the remaining part of the lecture. So we want to understand such matroids. And good tool for that, and also for the study of the entropy region and its closure, is the convolution. Convolution is a binary operation on polymatroids. So I have two polymatroids. On the same set. And the second I will assume is modular, always. Modular, to remind, this is the sum of GI is GN. If it's not modular, then it doesn't work, or I don't understand what's going on. And this is defined as this will be a new polymatroid. So taking two, I construct the third one, and this will be defined like minimum. I have to define the value. I divide the set I into two pieces, and look what the rank of one and rank of second. So take J, this will be the division. Here is HJ plus G I minus J. And one minimum for every. People who know convex analysis would recognize that this is very similar to the so-called infinimal convolution. If you do conjugate to a sum, then it's infinimal conjugate to convolution to the individual conjugates. But I don't know what is conjugate in this setting, yes, I mean, in this discrete setting. So it's natural. I learned this from a paper by Lovas, 82. But it's even mentioned in Fujishige's paper, 78. He didn't call it convolution, he had some different word, and he didn't develop the situation. He just mentioned that this is interesting. That was the first paper making connection between the polymatroids and entropy functions, yes. And this was quite an extensive review of submodularity.
Why is it called convolution?
Why it's called convolution? Probably it's in parallel to the continuous case. Because
Is it symmetrical?
it is, it's commutative, yes, you can do it the other way around, yes. It's commutative and it's associative, yes. That's important, I will use it, yes. So let's have a look what's going on. So first situation to see is, first example, is when this G is big. So all values are bigger than of H. So what happens? That bracket on the right is Hj plus, and this is modular. That means sum of Gi over Ij. That's where I need modularity. And this is greater or equal than Hi. And then by some modularity of H, this is greater or equal than. Yes? That means the minimum is attained when J is empty. And then H is equal to H convolution G. So this G doesn't harm. If G is big, G must be small. Well, so let's have a look at when one value is smaller, yes? So I'm assuming Gi is smaller than Hi, and the remaining are bigger, yes? Gj is greater or equal than Ij for J different from A. Then this bracket is, well, depends on I. Yes, if I have I, and I'll assume this peculiar element is not in I, if this is simpler situation. If it's not in I, then I repeat the previous thing, yes? Because it doesn't come into consideration. So then I can conclude that Hi is equal to H convolution Gi. And if I is in I, then, well, the bracket is, depends where this small I comes, whether to J or to the complement. And so if it comes to the complement of J, then I do the same trick. So and if it comes to here, well, I do again the same trick. So I at the very end I compare only two numbers, and this is H of I and H of I minus small I plus Gi. I mean, this is the whole, I should write it that way. So in the situation when all values are bigger but one, then it's easy to compute the minimum. It's only minimum of two numbers. And what does it say in the language of entropy functions? So assume I have few minutes. It's okay.
Yeah, I mean, yeah.
Assume H is entropic. And I is the special index, yes? So I have a special variable for that index, and the entropy of this is bigger. The entropy of this is bigger than GI, or maybe strictly. This is like if I wanted a variable with smaller entropy, which is a function of that variable, and behaves well in such a way in entropies. And this means that it should be the kind of most free variable. Of course, it's not possible, because if this psi I takes only 2 values, then functions of that are trivial. Yeah? Either the variable itself or constant. But if this has many values, then the variable has many functions, and maybe some of them has a smaller entropy and behaves nicely according to this formula. So this is like finding most free point, yes, coming from, it's not possible to see most free point. So maybe I stop at this moment, and I will continue with the development later.